Okay, so yesterday we were looking or just starting to look at rational equations and how to graph rational equations. And the first thing that we looked at were vertical asymptotes, what a vertical asymptote was, and then how to identify where a vertical asymptote was on that rational equation. A rational function. Okay, and so we defined what that looked like. And so let's say we have R of X. We said it was equal to some polynomial, P of X, all over some polynomial, let's say call it Q of X. Well, P of X was a polynomial, and so we could write it in that form that we had written out before by the definition, a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot, 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 a sub 1x plus a sub 0. Let's do the same thing. Q of X is a polynomial, so just by that definition, you have that b sub n. Let's now write it as x to the n. Actually, we don't know that they're the same, so let's say m here. Plus b sub n minus 1, x raised to the m minus 1, plus dot, 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 b sub 1x plus b sub 0. And the values of our exponents, they had to be positive integers. So I don't know why that's coming up. Are positive integers. Okay, so again, our vertical asymptotes that were occurring at x equals the values which make the denominator equal 0. But not also the numerator. So we already talked about that. If it made both of them equal to 0, then it was an open circle. It was still undefined for a rational function, but we actually had an open circle on the graph versus a vertical asymptote. And so now let's get into what are called horizontal asymptotes or slant asymptotes and how to find those. So horizontal asymptotes . First of all, what are they? So basically what a horizontal asymptote is when your graph is either going to positive infinity or negative infinity, your graph is going to be hugging some horizontal line. So it's not going to be shooting off all the way like to positive infinity or down to negative infinity like it was for some of the functions we were looking at before with graphing the polynomials. Here, it might hug some certain horizontal line instead. So for instance, we could write this as the limit as x is approaching, let's first start with positive infinity, of our rational function p of x over q of x. There's going to be a horizontal asymptote going to exist if this is equal to some value of a. So let me just write what that's basically saying. And so if you have some horizontal line, let's say that this is your value a. I'm going to put a dotted line here. because it's a horizontal asymptote. So this is a horizontal asymptote, and we could write it, that equation in y equals a. And so your graph, as it's going to positive infinity, it's going to be getting closer and closer to this horizontal line at a. So when we were talking about vertical asymptotes, I told you a line, your graph could never cross a vertical asymptote because that's where your function was undefined. Horizontal asymptotes are different. Horizontal asymptotes, it's possible that that graph crosses that horizontal asymptote, but if it does, it's going to start hugging that line on the other side of it. So it's possible that this came up here, oops, and started hugging it on the other side of the horizontal asymptote. We could find that point of intersection if we set our original function, p of x over q of x, equal to the line y equals a. So if we did this, we could find this point of intersection. That would give us the x value. Well, we know the y value, which is a. So if this point exists, then you can find it by figuring out p of x all over q of x equals a. So if you get a false statement like 5 equals 6 or something that's untrue when you were solving there, then we know, or an imaginary number, then we know that at that point, if that graph didn't cross that asymptote and it was just hugging it on the side it was coming in from. Okay, so that's what a horizontal asymptote would look like. So it's possible that we're looking at it as the limit as x is going to negative infinity. Let's look at that. So as the limit as x is going to negative infinity of your rational function, p of x over q of x. And this is going to go towards some y value. So it's possible it's going to the same horizontal asymptote. And so it's possible that in this case, maybe we have something down here and then it's hugging it this way. And so this 2 would equal to a. So as your x is getting smaller and smaller and smaller, heading to negative infinity, your y value is getting closer and closer to this value of a. Possibly touching and crossing, but not necessarily. Okay, so how to find horizontal asymptotes? It has to do with the degree of the numerator and the denominator. So to find horizontal asymptotes, look at both the degree of the numerator and denominator. Okay, so up here when I kind of divide it generically, let's use that. See if I can pull that. Let's use that as when we're doing the definition. So we can just name our degrees from this. And we also can see our leading terms and our constants. Okay. I'm gonna see if I can grab this and pull it down. Oh, come on. Uh-oh. Darn it. Let me undo. I was getting so excited that it was working. There we go. Come on. Darn it. Yay. Here's a scenario. Persistence pays off. Same thing with your courses. Okay. And for some reason in life, things just aren't as easy as you want them to be. They always tend to be a lot more difficult. And so just continue to work at it and you'll get it. Okay. So anyways, horizontal asymptote has to do with the degree of the numerator and denominator. And so notice in this case, the degree of our numerator. Remember that was the largest power. That was the largest exponent of the term of your polynomial. And so in this case, let's say it's n. Degree of the numerator is equal to m. And if we look at the degree of the denominator, this is m. Okay, so there's 3 different cases that can happen with those degrees. They can either be equal to one another. The numerator could be larger than the denominator, or the numerator could be smaller than the denominator. And depending on the case, it depends on if you have a horizontal asymptote or what we call a slant asymptote, which I'll talk about more in a minute. So if they are equal to each other, okay, so you have 3 different cases. And we're looking at when they're equal to each other. So when n is equal to m. If this is the case, these are horizontal asymptotes, so the lines are horizontal. We write the equation in the form y equals. And so if they are the same, then the horizontal asymptote is going to occur at the leading coefficient. So then there is a horizontal asymptote. And it occurs at the leading coefficient of our numerator. So remember the leading coefficient, that was the number in front of the variable raised to the highest power. So we have a sub n, all divided by the leading coefficient of our denominator, which is b sub n. Okay, so there's one scenario. The other scenario is when our degree in our denominator is bigger than our degree in the numerator. So to write that, we know we're saying that the degree in the denominator, n, this is a smaller number than the degree in the denominator, m. So basically what's happening is because the degree in the denominator is larger, it's blowing up faster. And so if you have some number over a huge number, so 1 over 10, that's 1/10. If you have 1 over 100, that is 1/100. It's getting smaller and smaller and smaller. If I have 1 over 1,000, that's 1,000ths, 0.0001. So it's getting closer and closer to 0. And so if the degree of the denominator is larger, then you're going to have a horizontal asymptote, and it's going to be at the line y equals 0. And that line y equals 0 is your x-axis. So then, again, there is a horizontal asymptote. I'm going to call it HA for now on, so I don't have to write it out. And it is at y equals 0, the x-axis. Okay, so the last case scenario is when our degree of our numerator is bigger than the degree of our denominator. So in this case, n is bigger than m. If this is the case, no horizontal asymptote occurs because the degree of the numerator, it's growing faster than the degree of the denominator. And so that's either going to be blowing up to either positive infinity or negative infinity, depending on the coefficients in front, if that gives us a positive or negative. This actually gives us what is called a slant or an oblique asymptote in some cases. But let's first put here that no horizontal asymptote occurs. And there may exist a slant or oblique asymptote. Okay, notice here, it's impossible to have one of these oblique asymptotes or slant asymptotes and have a horizontal asymptote. So you're never going to have both. Oblique slant, or I meant to put oblique. So either both horizontal and oblique / slant asymptotes cannot both occur. Right? It's impossible for the degree of the numerator to be both bigger than and then also smaller than the degree of our denominator. Okay. So those can't overlap. Okay. So let's look at the case. Let's look at a couple of cases. Actually, let's talk about these slant or horizontal asymptotes. To find the slant or horizontal asymptote, it depends. If the degree of the numerator is just 1 larger than the degree of the denominator, then you're going to have a slant asymptote, which means basically you have some line, y equals mx plus b, where your graph is going to start hugging this line as it comes in and is going to infinity, or maybe possibly negative infinity. And so there's a couple cases. If the degree of the numerator is just 1 more than the degree of the denominator. So technically, because we had defined things before, we can write this mathematically, and I don't have to be spending all this time writing this. And you're going to start seeing a lot of more shorthand in math while you go on. And so basically, our degree of our numerator, which we called was n, and would have to equal 1 more than the degree of our denominator. Well, we said that the degree of our denominator was m plus 1. If this is the case, then you're going to have a slant asymptote. Oops. Then a slant asymptote exists. And this occurs at y equals the quotient of p of x divided by q of x. So you're going to get some form of a linear line, y equals mx plus b. We can call it ax plus b here. If your numerator is larger, but it's larger than more than 1 degree, then we have what is called an oblique asymptote. So if the degree of the numerator is larger than 1 more than the degree of the numerator. Okay, so let's write that mathematically. So that's saying the degree of my numerator, which we called was n, was greater than, but not equal to, it had to be more than that, n plus 1. If that was the case, then we had a, what they call a Bleak asymptote. Okay. So we could get it the same way that we did before by doing long division. But remember, when we were looking at polynomials, so we're going to get some polynomial there other than a linear equation. And when we were looking at polynomials, it was really just the leading term that determined the end behaviors of our graph. So basically, if we look at your coefficient y is equal to the leading term on top, which we called a sub n, x sub n, all over the leading term on the bottom, b sub n over x sub n. then we can just look at using your rules of exponents. Remember, if you're dividing, you have the same base. This is strictly multiplication in between in the numerator and denominator. We can do this. We just subtract the exponent that's on the bottom from the top. And so this would equal a sub n over b sub n, that leading coefficient, x raised to the n minus m power. Just write it here. Okay, so this was only you can do this. You have to use long division the other way. You can only do this if your degree of the numerator was more than 1 than the denominator. I wanted to check one thing back up in the original notes to make sure I hit on it. And I did. Okay, so we're going to kind of put all of this together, what we're just doing. Well, maybe I need to review some long division of polynomials, but we're going to put this all together today and be able to graph these. And your book broke this up into 2 different sections, 5.3 and 5.4. I'm kind of going to incorporate, when we look for our asymptotes, graphing it at the same time, which is really what 5.4 goes into. So I'm going to be kind of intertwining both of these sections together when I teach you. Okay, so let's look at a following. Let's say you had g of x. This is equal to x cubed plus 1 all over x squared minus 5x minus 14. Okay, so let's say part A says find any vertical asymptotes that exist. Or actually, let's find the domain, which will help us find those vertical asymptotes. So remember domain, we are looking for trouble spots. Trouble spots in this rational equation is going to be any value which sets our denominator equal to 0, any real number that sets it equal to 0. And so we're going to try to find when is x squared minus 5x minus 14 equal to 0. And so looking at this is a quadratic equation. So first thing I would look at is I would try to factor this. I notice there are 2 numbers that multiply to give me negative 14 and add to give me my middle term coefficient of negative 5. So x minus 7 all times x plus 2. This is equal to 0. So looking at this, x cannot be 7 and x cannot be negative 2. So just so that you kind of get used to this, I noticed that your book tends to use set builder notation a lot more than interval notation. Interval notation is really good, and you'll see that a lot more when calculus and stuff. But set builder notation is also good. So basically this is saying you have a set. So sets are denoted by curly brackets. That's how I call them. And then we're going to denote our variable that we're talking about. And so in this case, it's x. You usually see this vertical line in here. And that's giving you some rule about that variable that you just said. So it's x. And you can read this in English. That vertical line mathematically says such that. So it's a set X such that we have to put on two conditions for X. X just can't be 7, and X cannot be -2. Okay, so part B, let's find the vertical asymptotes. So again, vertical asymptotes occur when the denominator is equal to 0, but not also the numerator. And so it's helpful to be able to factor both the numerator and denominator if possible. Thing is, I noticed that the top, it's actually factorable, but I also can see that it's not going to have a common factor with the denominator. And I'll explain that reasoning in a second. But g of x right now is equal to x cubed plus 1 all over x minus 7. We already factored the denominator to get where it was equal to 0, and all times x plus 2. Okay, so when you're looking at factoring, it depends on how many terms it is. It's kind of how you approach on how you would factor something. And so looking at x cubed plus 1, if you only have 2 terms, you're going to look to see if it's a difference of squares or a sum or difference of cubes. And so I notice I have a cube on my x, so this is an x cubed. And I notice that 1 can be expressed as 1 cubed. So this is a sum of cubes. And so just kind of review real quick. Sum of cubes, there's a formula, and they're factorable. So if you had a cubed plus b cubed, this factors as a plus b, all times a squared, opposite sign than what you have here, minus ab plus b squared. So the sign in between this a and b are always the same as this, always different, and always positive. If it had been a minus in between the cubes, so same sign in between, so this would be a minus b. So it's a squared, the square of the first term that you would have gotten to get that, cubed. Always opposite, so plus ab, always positive, plus b squared. So like I was saying, I could tell by that, knowing this rule, and that's factorable, that it's just not going to have the same factors. Also know with cubics, sum and difference of cubes, that these quadratics in here, the trinomial, they're never factorable over the real numbers or integers. I'm not sure, maybe it's reals, but it's just not factorable. We'd have to use the quadratic formula. And so when you're looking at x cubed plus 1, and I'm kind of giving you a little bit of an algebra review lesson. So I know my a value in my case is x, and my b value in this case is 1. And so this will be factored as x plus 1. So right there, that's not a factor of this, x minus 7 or x plus 2. And then we have whatever your a value was, in this case is x squared, so x squared. Always the opposite sign, so it's minus ab. So a is x, b is 1, 1 times x, or x times 1 is x. Always positive, plus this b value, which is 1 squared. 1 squared is 1. And there's no number that multiplies to give you positive 1 and adds to give you a negative 1. Okay, so vertical asymptote then, only values that set the denominator equals 0 are x equals 7, and x equals plus 2 is 0 at -2. Okay. So does the graph have a vertical, not a vertical, have a horizontal or oblique asymptote? So I believe that a slant asymptote is also an oblique asymptote, but it's just a linear equation, and so it also has a special name like which is slant. So for instance, rectangles are the broader range of things, but squares are also rectangles, but they are special rectangles. Okay, so does this have it? So let's go back up and look at our degree of our numerator and the degree of our denominator. And so if we look at our degree of our numerator, notice that we have degree 3. And if we look at our degree of our denominator, we have degree 2. So the degree of our numerator is larger than the degree of our denominator. So it's not going to be the x-axis, y equals 0, because they're not the same. It's going to be a slant asymptote because that degree of the numerator is just one more than that degree of the denominator. So it has a slant asymptote. Okay, so let's find the asymptote in part C. Okay, so let's look at our equation again of g of x. So our function was equal to x cubed plus 1 all over, it was x squared minus 5x minus 14 before we factored it. And so if the degree of the numerator is larger, then we're going to want to use long division if it's just one more than the denominator like we discussed it was. And so when you're doing long division, so we have what we're dividing by, which is x squared minus 5x minus 14 divided, and we're dividing into x cubed plus 1. And so if there's any terms in here that don't it's not in, okay, so you should be in descending order of powers, and if any terms are missing with those exponents, then you want to put a 0 there. So notice we have an x cubed here, but there's no x squared term and there's no x term. And so let's put in there kind of a space holder. And so we're going to write, this is called our dividend, x cubed. I'm going to put a 0x squared in here as a placeholder, plus a 0x, and then we have our constant plus 1. So long division, really all you're looking at is the first term in your divisor, which is x squared. We're always using this to determine what we're going to use to multiply. And so first thing you're looking at is x squared times what would give us this bottom term or first term in our divisor, which is x cubed. And so an x times an x squared is an x cubed. And so we're going to want to put an x there. I tend to put it anywhere, but I looked before and sometimes people put it just above what they originally, that term. So this was an x, so I'm going to put it above here. So remember when you found that number, when you're doing it with just numbers, you multiplied it by this and you put that underneath your number. So we're going to do the same thing, but we have to distribute this, what we've determined, to each term. So x times x squared is x cubed. X times negative 5x is negative 5x squared. And x times negative 14, that's negative 14x. So next step in long division is that you subtracted that value off from what was above. But you're subtracting off more than just one term or a number. You're subtracting off 3 terms. And so we have to be careful with the sign. So this is x cubed minus x cubed, which we wanted. We wanted that to cancel, and that's why we chose this x. But here is really 0x squared, but it's going to be plus, it's the opposite sign. So 0x squared plus 5x squared is 5x squared. Distribute the negative here. So 0x plus 14x. So next step, long division, if there's anything left, any more terms left underneath, then we need to bring it down. So there is one more term left up here. And so we have to bring this down. Let's bring it down and write it with what we got here. So plus 1. And we start the process over. So again, you're going to look at your first term. Our first term again is x squared. But this time we're looking at x squared times what is going to give us this first term of what we had gotten when we did the subtraction. Well, I know 5 times x squared would give me this first term, 5x squared. It's positive, so I'm going to just write the plus 5x in here. And so let's distribute that to all 3 terms to get what we're going to put underneath here and subtract. So a 5x times the x squared is 5x squared. Again, we chose that just so that that would be the same and cancel out. But it has to distribute to the negative 5x. So 5x times negative 5x is negative 25x. And 5x times negative 14. Well, 14 times 5. Okay, well, 5 times 4 is 20. But something happened. What do I do? Oops. I don't know why I put the 5x there. It's just a 5, right? Five times x squared is 5x squared. If I had an x there, that would have been 5x cubed. 5 times negative 5x is negative 25x. 5 times negative 14. Okay, again, so 5 times 4 is 20. Put my 0, carry my little 2. 5 times 1 is 5, plus the 2 I carried is 70. And that would be positive, minus. Okay, so again, we're going to subtract that value off. Eeks. Not again. And so if we subtract that value off, we get back 5x squared minus 5x squared is 0. 14x, but this negative distributive makes this really positive 25x. So 14x plus 25x is 39x. Distribute the negative. And 1 plus 70 will give plus 71. Okay, so this is actually our remainder. But in the directions, it told us that we only really had to look at our quotient. So the quotient is what we got that we were going to multiply by. And so we're going to have our slant asymptote is the equation y equals our quotient. And so the slant asymptote is y equals x plus 5. Okay, so putting everything together that we're learning and graphing these rational functions. So it's really helpful that you determine your domain, determine where your vertical asymptotes are, where any horizontal asymptote occurs if it does, or slant or oblique asymptote. And then finding intercepts are also important points that are helpful. And so let's find our intercepts. So find X and Y intercepts. Okay, so notice that our y-intercept this is when we let x equals 0. And so let's plug in 0 wherever we see an x. We're going back into our original equation, g of x, which was this x cubed plus 1, so 0 cubed. So let's just put a parentheses wherever we see an x. And so we have x cubed, so parentheses cubed, plus 1, all over x squared, so parentheses squared, minus 5, so 5 parentheses minus 14. Replace that all with 0. So basically we're left with the constant in the numerator divided by the constant in the denominator, always in this. And so the constant of the polynomial in the numerator over the constant of the polynomial in the denominator, which is negative 1 over 14. Okay, so we have 1 point. So when x is 0, we got negative 1 over 14. So I know that's pretty small, but to me it makes more sense if I have that in decimal form. So let me just approximate it. So that's about negative 0.07.
Professor,
Yes.
this is kind of a weird thing, but after we're done with this problem, is there a way you can go on Desmos and show us what each one would look like on the graph?
Of course. Yes, I would love to do that. So once we're done graphing it, we're going to compare it and match it and show and look at the asymptotes. So that would be good. Y or x-intercepts. So x-intercepts, when you're looking at a rational function and you're trying to find the x-intercepts, well, that's when y is 0. So think about it. If you multiply and you clear your fraction and multiply both sides by the denominator, 0 times the denominator is going to cancel out and you're just going to be left with a numerator. So really when you're looking for the x-intercepts of a rational function, you're really just worried about when the numerator is equal to 0. So we're only worried about when is x cubed plus 1 equals 0. So we talked about solving different types of equations. We could isolate our x cubed here because it's the only x term in here, and we could take the cube root of both sides. So if I subtract 1 on both sides, I get x cubed equals -1. Take the cubed root of both sides, I would get x is equal to, I only have to worry about that plus or minus when it's an even root, -1. And so the same number that you can multiply by itself 3 times to get -1 is -1. So we have a x-intercept at the point -1, 0. Okay, so next step when you're graphing these, put it all together. So you're going to want to graph all your asymptotes you found, and you want to graph your intercepts. And then from there, it usually comes out pretty fast. You just have to plot a couple of extra points on each side of a vertical asymptote, and then things, you can see what are going to happen because the asymptotes are there to lead you. And so let's kind of put it together. So this is F. Sorry, I need to put that glove back on because my hand's starting to get sticky. Okay, so this is part F. We're going to graph. We had 2 intercepts, vertical, I'm sorry, yeah, we did have 2 intercepts. We had one at -1, 0. And we had the y-intercept was -0.07. So really close to the origin. And then we had vertical asymptotes. That was +7, I believe, and -2. So let's just draw those dotted lines there. And then at 7, so 1, 2, 3, 4. And then we also had a slant asymptote, and I believe that was y equals x plus 5, or maybe it was -5. So let me just check. It was x plus 5. Well, it's already in slope-intercept form, so I can see that my y-intercept is at 5. And I can see that my slope is 1. So for every one I go up, I'm going to go to the right one. Or I can think of it as go down, I go down to left one. I might need to extend this just so we can see what's going on. Okay, so vertical asymptotes. We can never cross a vertical asymptote because that's when the denominator is 0. And so looking at what's going on between each vertical asymptote is helpful. We already found our intercepts. So we already found a couple of points inside of here. The thing is, I don't know if my graph at this intercept for x is going to cross it or if it's going to turn around. Well, actually, we can determine that by the multiplicity of that 0. And if we look back at that multiplicity, that was just 1. Actually, instead of me saying that, let's just test it, and let's just test it. So I can tell if it's going to cross here or if it's going to come back down around if I choose any number in between my x-intercept and my vertical asymptote. And so let's check points. And so you are going to have to plot some points. So knowing what your y value is, again, is helpful. So this was x plus 1 all over, I don't know if it's easier in factored form, maybe x minus 7, x plus 2. And that was actually x cubed plus 1. So if we plugged back in -1/2 in here, we can see if this is going to be a positive. Actually, we're really just curious, is it positive or negative? Well, and I can kind of do some reasoning about that real quick by knowing -1/2 cubed. That's a negative number, but it's a negative number that is smaller than 1. And so I know I'm going to have positive in my numerator. -1/2 minus 7 is negative. -1/2 plus 2, that's positive. So this is a positive over a negative, which is a negative number. And so I know at, oh shoot, I chose a number between -1 and 0. And I knew that that was going to be a negative number because of my y-intercept. Okay, that didn't tell me anything. I need to choose something in between -1 and -2. So let's do that also. So let's look at -1.5. I'm going to kind of do the same reasoning. So -1.5, let's look at what that is. That's probably bigger. Cubed, it is. That's -3.7 or -3.375 plus 1. So that's a negative number in my numerator, all over. So -1.5 plus -7, that's negative. -1.5 plus 2, that's positive. So this is a negative over a negative, because our denominator, a negative times a positive is negative. Negative over a negative is a positive number. So this is telling me that in between here, -1.5 and -2, I'm going to be above this axis. I can find out exactly by plugging in the numbers, but I want to show you on Desmos kind of a quicker way to do this, and that's something that's also will be useful in calculus class. So we'll find that number in a minute, but we have a general idea and we know it falls above this. So let's just kind of talk about the piece that is in between -2, x equals -2, and x equals 7. You found all the x-intercepts. You know that this graph cannot come back up around because, or it might come back up around a little bit, but it cannot cross this x-axis again because you found all the x-intercepts. And so we know that this piece, and there's a vertical asymptote here, so it can never cross it. And so it's going to have to start hugging it down here. Same sort of reasoning. We only know there's one x-intercept. And so I can't take this piece on the left of -1, but before this vertical asymptote, and turn back around and cross the x-axis. I can never cross a vertical asymptote, so I'm going to come back up, and I'm going to have to, or I'm going to come up, and I'm going to just have to start hugging this vertical asymptote. Okay, so it's not going to hug the slant asymptote in this piece in between -2 and 7. It could hug it. It probably is going to hug it on the left and the right. I just don't know if it's above or below this. And so again, this is where testing a couple of points is helpful. Okay, so let's choose something to the left of -2. We know there's no x-intercepts over here, and so let's try -3. This might help me a little more in this case, actually, if I figure out more of the value. -3 cubed is -27 plus 1 all over -3 minus 10, -3 minus 7 is -10. -3 plus 1 is -1. So this is -26 all over +10, which is -2.6. Just want to make sure my math is right. Okay, so that's telling me it's below the x-axis. And so that tells me, again, I have a asymptote on this side. So it has to be shooting down towards x equals -2 as x is approaching -2 on the left. It's not going to cross this x-axis. And so it's going to turn around in here and it's going to start hugging this slant asymptote. So my guess is when we choose a value, so just choosing one value, I could determine all that about the shape of the graph. So choose one value on the right of 7, the other vertical asymptote, so maybe 8, and let's see what we get back. I'm thinking we're going to get a huge number and that it's going to be above this slant asymptote, and we're going to have kind of that U shape again in there, kind of slanted U. So 8 cubed, that's pretty big, 8 cubed. That's 512 plus 1 all over 8 minus 7, so that's 1, and 8 plus 2, that's 10. So that's 513 all over 10, which is 51.3. Yeah. So like I said, it's above the slant asymptote. We know the vertical asymptote is here, so it's going to have to start hugging it. I couldn't come below because it couldn't cross this x-axis. There were no x-intercepts there. And then I'm going to turn around and I'm going to hug this as x goes to infinity. So it is possible, again, that the graphs can cross, like, and you saw it right here, that it crossed this asymptote, this slant asymptote. So it's possible that it crosses a slant asymptote. It's possible that it crosses it over here and hugs it. I wouldn't know that unless I solved for those values. But let's take what we just did and let's plug it into Desmos and see our graph. So let's see. Weeks. I need a new window. Okay, so Desmos, oops. Okay, so we're going to define our function. And this was, we need parentheses around the whole numerator. And so we got parentheses, and then we have x cubed. So x, it's raised to a power. And so to do powers, it's that little caret symbol. Where is it at? Cubed, and then get out of that, plus 1. X. Okay, plus 1. I had to get out of the exponent. And then I'm dividing this all by, so divided by, it already put me underneath the denominator, so I'm okay. I don't have to put parentheses there. So I have x squared. I'm sorry, I'm painfully slow at this. Might be a good thing for you guys. Plus, or was it minus? Where's the minus? Minus 5x minus 14. Okay. Let me change my y values, because we know when we had x equals 8, we had like 50 something. So maybe wish I could just let's do 100. Oops. Which is like the graph we got. So the graph we had was that, whoops, things shifted. Came down. We said there was a vertical asymptote here. They don't show the dotted line, and they shouldn't show the dotted line. If we put our value in here, you can see this is -1, 0. That's where it's crossing the x-axis. That's what we found. This point over here, I don't know if I can see the y-intercept. It was really small. We talked about, yep, there it is, 0, and then the -0.07. This here is an important point. This is where actually you have a max. So we have a absolute max here. That's where it's changing direction from increasing to decreasing. And this is following both the asymptote on the left and the right of x equals 2 is hugging that line. X equals -2. X equals 7. So this is where our vertical asymptote was here. On the right, it's hugging it down below the x-axis, or sorry, the right of x equals 2, it's hugging it above. And x equals, I'm sorry, it's 7, not 2. It's hugging it below. And then the slant asymptote, if we kind of look at this, let me graph at the same time x equals plus, y equals plus 5, that slant asymptote. Oops. So x plus 5. And a couple other ones. Let's look at x equals was it, -2? And x equals 7. And so you can see our graph is the red one, and our graph is hugging our vertical asymptote, which is x equals -2, the green line, vertical line, x equals 7, this purple line. And it's hugging our line y equals x plus 5, that slant asymptote. Pretty darn cool, isn't it? It's not too bad. So hopefully that wasn't bad. Okay, so personally, if you were taking this test on paper in class, I wouldn't have I wouldn't have choice A, B, C, D. And so when you're taking the exam and you're graphing something like this, I want you to be showing me the steps on how you got the points and stuff and where you are. I want you to graph it, and then looking at your graph, then you can choose which graph represents what looks like yours on my math lab. So just practice graphing it when you're doing the homework and not rely on looking at the graphs on my math lab to figure it out. Okay, so any questions on this? Let's do at least one more. And with that one more, and so like I said, we're kind of putting all together 5.3 and 5.4 in your book. I don't like how skinny my pen gets sometimes, so just making a new page makes it much better. Okay, so let's graph the following. And we're given r of x is equal to sorry, we got important decisions here. Which one looks good? I don't know. Let's try this one. X squared plus 3x minus 10. And this is all over x squared plus 8x plus 15. And it asks you to graph the following. Okay, so we want to, in order to graph this, we want to find vertical asymptotes, and we want to find horizontal or slant asymptote or oblique, depending, and intercepts, and then start putting it together. So let's start by factoring both the numerator and the denominator, if possible. And so x squared plus 3x minus 10, there are two numbers that multiply to a -10 and add to a +3. So we can factor this as x plus 5, x minus 2, all over. And so the denominator, looking at factors, something that multiplies to 15 adds to 8, so 5 and 3, x plus 5, x plus 3. Our domain is x such that we can't have any value set our denominator equals 0. So x cannot be -5 and x cannot be -3. I also noticed though, both of these values, x equals those numbers, are not, and I shouldn't put does not equal, not just equals. I noticed that those are not both vertical asymptotes at those values because x plus 5 sets both the numerator and denominator equal to 0. And so when we're graphing this, we can graph the equivalent function, a simplified form, except that there's one thing that we have to worry about is at x equals -5, there's an open circle here. So we can find that open circle. Let's look at the simplified form, which they're not equivalent totally, but almost. If we looked at f of x equals the simplified form x minus 2 all over x plus 3. And let's go in there and plug in -5. So f of -5 so plug in -5 wherever you see an x in f of x. We get back -5 minus 2 is -7 in our numerator, all over -5 plus 3, which is -2 in our denominator. So this gives us 7/2, which you have an open circle at -5, 7/2, which is 3.5. The value though, x equals -3, that does not set that denominator or numerator also equal to 0. And so that is a vertical asymptote. So we know we have a vertical asymptote at x equals -3. Okay, so depending on degree of numerator denominator depends on if we have a horizontal asymptote. If the degrees are the same, they did have a horizontal asymptote, and that's where we looked at the leading coefficient of the numerator all over the leading coefficient of the denominator. And so if we look at our leading coefficient of our numerator, that's 1, divided by the leading coefficient of our denominator is also 1. So we have a horizontal asymptote. Horizontal lines are in the form y equals 1 divided by 1, which is 1. And so now let's look at intercepts. So if we look at r sub 0, so we plug in 0 back into our original equation. Remember, it's just going to give us the constant on the numerator, which is -10, all over the constant on our denominator, 15. So this reduces, both of them have 5 in common, so this would be -2/3. And then for our x-intercept, that was where we only worried really about when the numerator equals 0. It's in factored form. X plus 5 can't be 0, because I also set the denominator equals 0, and it's undefined there. But we are looking at just then maybe when x minus 2 is 0. And so that's going to give us when x is equal to 2. So we have some points here. 0, -2/3, which I believe is 0.6. Yeah, -0.67.
How did you get -10 over 15?
God, sorry, I got a tickle in my throat. Plugging in 0 for x, if you have 0 squared plus 3 times 0 minus 10, you're only left with a constant in the numerator, negative 10. 0 squared.
Oh, okay.
Yeah.
So for the whole value of Rx.
Yeah.
Okay.
So plugging in 0 for x, it simplifies down to the negative 2/3. Okay, now I'm tearing up. So we had that. That is our y-intercept, and then our x-intercept we got by just setting our numerator equal to 0. The one piece of our numerator, x plus 5, of our original function, that couldn't be equal to 0 because that also set our denominator equal to 0. So only really what we had to worry about was when is x minus 2 equal to 0. And so adding 2 to both sides, we get x equals 2. And so we know we have a point x-intercept at 2, 0. Okay, so let's put together so far what we have. We have our asymptotes that occur. We have our intercepts that occur. And so graphing all of those together. Oh, no. Okay. So vertical asymptote was at -3. So I'm going to put a dotted line at x equals -3. Horizontal asymptote was at 1. So I'm going to put a horizontal line at 1, dotted line. And then our intercepts, we had x-intercept at 2, 0. And we had a y-intercept at 0, -6.7 about. So just knowing those 2 points on the right-hand side of this vertical asymptote, x equals -3, I can tell what that graph is going to look like. So because it has to always hug a vertical asymptote, can never cross it, and I don't have any other x-intercepts on the left here, it has to come down and start to hug it. Again, there's no other x-intercept, so I'm going to have to come up here and start to hug this line. If you want, it could be important to check over here a point. But like I was saying before, if you know about the factor, this factor on the bottom, or that factor in the numerator that set that equal to 0 had a multiplicity of 1, and so it's going to cross it. Knowing there's no x-intercepts on the left of -3, I can actually tell what my graph is going to look like there too. My graph is going to be above the x-axis, and it's going to be kind of a shape in here, like 1 over x was on part of our graph. But let's just show that. Let's just choose a value to the left of -3. 1 point will tell us that. So if we go back in and we plug in -4 into our function g of x, I think our function was called g of x. Nope, r of x. So let's look at what is r of, what did I choose? Uh-oh. Oh, wait. There's one other thing that we have to worry about. We have an open circle at -5, 3.5. So actually, I don't really have to check that. So at -5, positive 3.5. There's an open circle here. So actually, no, my graph is going to get really close to that open circle, never cross it. but it's going to follow that general pattern. Eventually, we're going to come down and start hugging this line y equals 1 on the left-hand side. So again, we can go and we can see if we plotted this on Desmos that we're going to get the same thing. So let's just do one more problem. During break, I'll put my keypad back on my tablet and I'll set those up so when we get back from break, we can just see what they look like on Desmos without me spending time in class doing that. So let's look at one more. So we looked at one where we had a slant asymptote. We looked at one where we had a horizontal asymptote. Maybe let's look at one where we have a oblique asymptote where it's greater, the degree is greater than one more than the denominator, the numerator is. Let's see if I can find one. I'm surprised they wouldn't give you one if they asked us to do one. They talked about it. Oh, here we go. H of x, this is equal to x squared plus 4 all over x to the 4th minus 1. Okay, so we want to find where it's undefined. We want to find vertical asymptotes and any other asymptotes. Looking at this, I cannot factor x squared plus 4 over the real numbers. I can factor x to the 4th minus 1. There's two terms, and I can make this look like it's a difference of squares. And so h of x, when we get back, this is equal to x squared plus 4 all over, well, the denominator is x squared minus 1 times x squared plus 1. So it goes a little further. I notice x squared minus 1 is still a difference of squares, and so this is x minus 1, x plus 1. And then we still have x squared plus 1 on the bottom. Sum of squares don't factor over the real numbers, but the quadratic numbers it does. So the values that set our denominator equal to 0 are x equals 1, and x equals a negative 1. So these are our vertical asymptotes. X squared plus 1 is only equal to 0 over the imaginary. If I wanted to write the domain, we would say the set x such that x is not equal to 1 and x is not equal to negative 1. Okay, so for horizontal asymptote, that is when the degree of the denominator, oops. I didn't do it. Oh well. That's when the degree of the denominator is larger. Degree of the denominator is larger here, right? And so I have a horizontal asymptote at y equals 0. There's no x-intercept. And you can see that by if you set your numerator equal to 0, x squared plus 4 equal to 0, and we solved, well, first of all, it doesn't factor. If we use our square root method, solve for x squared, take the square root of both sides, we get plus or minus square root of negative 4. No. Sometimes we want those values, the solutions, but not for an x-intercept. The y-intercept, well, if we plug in x or 0 wherever we see an x in our function, let's go back to where it wasn't factored. So we would have 0 squared plus 4 in the numerator, and we would have 0 to the 4th minus 1 in the denominator. So h of 0 gives me 4 all divided by negative 1, or negative 4. Okay, so we have two intercepts, or sorry, we have two vertical asymptotes. And we have a horizontal asymptote at the x-axis. So I'm going to do my dotted line on my x-axis. And we know at negative 1, so I'm going to make it a little bigger. We have a vertical asymptote, and x equals 1, we have another vertical asymptote. And we see that when y is, I have a y-intercept at negative 4. And no x-intercepts. Okay, so that tells me a lot about my graph. If I know I have one point in between x equals negative 1 and 1 that's below the x-axis, and it's not going to cross the x-axis, then it's going to have to stay below here. So I'm going to have some sort of a graph that looks like a parabola shape facing downwards in here. And it could be kind of skewed a little bit, and I actually don't know if it's changing direction right here at the top, but I have some sort of general idea what's going on. And then I know I don't have any x-intercepts. So again, I'm not going to be crossing this horizontal asymptote. So my graph is either going to be above the x-axis on the left of negative 1 or below the x-axis. Same thing on the right of 1, it's either going to be all above the x-axis or all below. And the only way I can figure that out is by plotting one value on the left of negative 1 and one value on the right of positive 1. And so let's go back to our original function here, h of x, and let's look at what's happening at h of negative 2. Well, if you square negative 2 times negative 2 is 4. 4 plus 4 is 8. So get an 8 in the numerator. If I raise negative 2 to the 4th power, negative 2 times negative 2 is 4, times negative 2 is 8, negative 8, times negative 2 is positive 16. And then I have 16 minus 1 is 15. So I have 8/15 at x equals negative 2. 8/15 is bigger than 0. And so I'm above the x-axis at negative 2. And so our graph will have to look like this on the side. So test what positive 2 would look like. Guess that wouldn't be there. And so looking at h of positive 2, well, we can actually use the fact that this is an even function. If this is an even function, I know this is an even function because h of negative x equals h of x. So that tells us it's symmetrical across we'll change your x values, that's across the y-axis. So it's symmetrical with a So actually without plotting a point, or I know it's metrical that the y value at x equals positive 2 is also whatever our number was up here, 8/15. So actually knowing it's symmetrical, they should kind of look like each other, mirror image across. That actually helps me know that too, that is probably this is gonna be my max of my parabola, because they have to be a mirror image across each other. Okay, so you get that general idea. Okay, so that's a good spot to stop for a break. Okay, so just like I was just mentioning to the class, I just, during break, put the equations we were just graphing on Desmos, and I wanted to show a couple different things. So the first graph that we were looking at was x squared plus 3x minus 10 all over x squared plus 8x plus 15. So we found that there was a value which set both the numerator and denominator equal to 0, and it was not going to be an asymptote. And I believe that was at x equals, let me think, plus 5, so -5. Notice here though on this graph, it doesn't show an open circle, and there should be technically an open circle there. X equals -3. That was another value that set the denominator equal to 0, but it also didn't set the numerator equal to 0. And you can see our graph is hugging this line x equals -3. It actually looks like it touches, but it doesn't actually ever touch or cross it. We also found that it had a horizontal asymptote because they both had the same degree. And you can see that our graph as x goes to -infinity is getting closer and closer to y equals 0. Same thing as x is going to positive infinity, it's going closer and closer to 0. We also talked about the version where because both the numerator and denominator had like factors, we could cancel it. And we said that they weren't identical, but very similar. The fact that the one above, which we were dealing with, was also undefined at x equals -5. But if we graph that function, if we simplified this by canceling those like factors out, notice that it's going to be the exact same graph that we have above. And so it overlaps each other. The only difference again is that open circle that we're going to have when x was -5. And you could plug that in to see what that value was. And then, if there's any questions on that before I kind of took it away, but I also have the equation for the other problem. And that was the equation x squared plus 1 all over x to the 4th minus 1. We found that it had vertical asymptotes. Let me change this a little bit so we can see a better representation. I don't know. Let me see if I can do it this way. Okay, that looks better. So this is the equation, the second equation we looked at, x squared plus 1 all over x to the 4th minus 1. We had factored the denominator, found values which set the denominator equal to 0, but not also the numerator was x equals 1 and x equals -1. So you'll notice you'll have your vertical asymptotes here if I plotted them. And they're hugging both of those. We talked about that it was an even function. If we plugged in -x wherever we saw an x, that it was equal to the original function. And so that meant that it was symmetrical across this y-axis, which it looks like it is. The degree of our denominator was larger than the degree of our numerator. So that tells you that you have a horizontal asymptote, and it's at the x-axis, the line y equals 0. Actually, y equals 0. And for some reason, we put y equals 1 in here. So if we look at that line, y equals 0, again, you can see that as a limit, as x is going to negative infinity, as x is approaching negative infinity, your value is getting closer and closer to 0. And as your x value goes to positive infinity, your y value is getting closer and closer to 0. We didn't find any x-intercepts, so that graph is never going to touch or cross that axis. So any questions on that? Can you guys hear me okay? Okay. One other thing I wanted to show you on here real quick, and I had mentioned that I wanted to show this. Let's see if I can get back. Let me just open a new page. So going back to Desmos.com, they have multiple different features, not just graphing, but you could put in your function and then you can evaluate it at different numbers. And so you don't have to spend that time, keep on plugging in, your value for X and doing all those different operations to see what it is. So let me see. They changed things around in this website, so it's not exactly how I had remember looking at it. Yeah, maybe this is it. Okay, so we had some of those functions, and let's look at one of them. What was it? X squared plus 3x minus 10. And this is all divided by x squared plus 8x plus 15. Let me copy that. I might be in the wrong place. Let's try this. Okay, so I am in probably the wrong place then. Might just be the scientific calculator. Okay, so it is. So on the scientific calculator, you can go in and you can define your function. And then once you define your function, you can go in and tell what values of x you want in here. And we talked about the y-intercept. When you plug in 0, it was the constant of the polynomial on top, -10, divided by the constant of the polynomial on the bottom, 15. We reduced that and we saw that that was -2/3, which this is giving the decimal form, which we rounded it to, but you can also convert that to a fraction, -2/3. So just something that's really helpful when you have to plot a lot of different points and you have a lot of different, that variable is in there a lot of times. And so it's just a faster way to do that. Okay. So I found one function, there's two examples in your book that does have where your denominator is larger than your degree of that is larger than your degree of the denominator. So let's look at one of those. And let me flip my screen. Take that off, sorry. And I can see that my hands are gonna, or my palm's gonna make it so this is not writing well. So let me just put this funky glove on. Okay, so we're looking at the following. Q of x, this is equal to x to the fourth minus 1 all over x squared minus 4. And it's asking you to graph this. Okay, so let's start out by factoring both the numerator and the denominator. So I noticed two terms in the numerator, and so I'm looking to see if there are difference of squares, and they are. And so this factors as x squared minus 1, x squared plus 1. And the denominator, it's also a difference of squares. So that factors as x minus 2, x plus 2. Numerator can be factored a little further. X squared minus 1 can be factored as x minus 1, x plus 1. Sum of squares can't be factored over the real numbers, so we're going to leave it as x squared plus 1 all over x minus 2, x plus 2. So our domain are all real numbers except values which set our denominator equal to 0. So x such that x cannot be 2 or x cannot be negative 2. Vertical asymptotes, those are values which set just the denominator equal to 0 and not both the denominator and numerator, and nothing sets both. And so we have a vertical asymptote, two of them, x equals 2 and x equals negative 2. So looking at this, it does not have a horizontal asymptote because the degree of the numerator is larger than the degree of the denominator. So that means it has an oblique asymptote. If it was more than 1, the degree of the numerator is more than 1 than the degree of the denominator, then it was where we were going to look at y was equal to the leading term on top, which is 1x to the fourth, divided by the leading term on the bottom, which is 1x squared. And so our oblique asymptote is close to x to the fourth over x squared. Rules of exponents, subtract 4 minus 2 gives us 2. So y equals x squared. Okay, so y-intercept, always the easier one to find. So plugging in 0 for x, so q of 0. Well, everything's going to cancel out in the numerator except for the constant, which is negative 1, all over Everything's going to cancel out when you plug in 0 for x except for the constant, -4. So -1 over -4 is 1/4. So the y-intercept occurs at 0, 1/4. The x-intercept well, if we set our rational equation equal to 0 and we multiplied both sides by our denominator, 0 times the denominator is 0. And so we're just looking at when our numerator is equal to 0. And that's actually easier to see when that was factored. And we have, actually, I guess it doesn't really matter. But we could have used the root theorem. But in factor form, we have x minus 1, x plus 1, all times x squared plus 1. So I'm looking at the values which set that equal to 0. So that's when x equals 1. And that's when x equals -1. We talked about things being factored as far as possible, and all polynomials can be factored. And this is something that we're going to be talking about soon in the rest of this chapter, is all things can be factored as linear factors and or quadratic, where those quadratic were not factorable over the real numbers, which that is not. So there's no real number that gives me x squared plus 1 equals 0. So we got our vertical asymptotes when x is 1, y is 0, and when x is -1, y is also 0. So we can put everything that's important together, our intercepts. We can plot those. We can plot our oblique asymptote and plot our vertical asymptotes. And then hopefully it will fall together and we can see what's going on. Okay, so x-intercepts, we're at x equals 2 and x equals -2. So we can denote that by dotted lines, a vertical line going through x equals -2 and a vertical line going through x equals +2. We have a graph where it's an oblique asymptote. So, and that is y equals x squared. That's a parabola that's centered at the origin. Let's see how we want to do this. Maybe not as wide for our y values. So when x was 1, y is also 1. When x is -1, 1. When x is 2, we would have 4. -2, 4. But this is not part of our graph. This is just our asymptote. Actually, it might not be that wide. I probably should plot some more points, but. And then we had points on the graph. Our intercept was 0, 1/4. And we had x-intercepts at 1, 0 and -1, 0. Okay, so looking at this and knowing where our values are and knowing what my multiplicity on my zeros are, I'm going to have a y-intercept here and we have a point here. So because its multiplicity is odd, I'm going to cross this axis. And again, we can test that by plugging in a point in here. And I know I have to follow my vertical asymptote. I can't cross it, so I have to follow that one. Same idea in here. If you also look at our equation, notice that this is an even function if you plug in negative x wherever you see an x, that's going to give you back the same function. And so I know this is also symmetrical across the y-axis. So the next thing I need to do is plot some points on either side of -2, but my guess is because of this having an oblique asymptote that we're going to have these like parabola shape in here, kind of a weird parabola shape. And it's symmetrical, so it'd have to be on the other side, but I want to make sure, and so let's just plot a couple points. So if I plug in, let's say I was on the other side of -2, so let's say -3. -3 raised to the 4th power minus 1. I think that's 81. It is. So that's 81 minus 1, which is 80, all over -3 squared is 9. 9 minus 4 is 5. So that's going to give us 18. It's a positive number. And because it's even, yeah, that's not how you write because. Because q of x is even for every xy point, then there also has to be the point -xy. So at +3, we also know we get positive 18. Okay. So -3, we get positive 18, which is way up here on my graph. So just to get a kind of general idea, we know it's going to look like this. And pretend that's symmetrical. Okay, so that was all of 5.3 and 5.4. 5.5 talks about polynomial and rational inequalities. So we had already talked about quadratic inequalities and graphing those quadratic inequalities and seeing where is that graph, what values of x is that graph above the x-axis, if it was greater than or equal to 0, or where is that graph falling below the x-axis, and determining those x values. And then I mentioned that there's also a way to do that algebraically. And that's what you guys have done in the past algebra classes, is solve that algebraically. So I'm just going to do a quick review on how to do that. So we get, and this is section 5.5 in your textbook. So this, our polynomial and rational inequalities. Okay, so far in this chapter, we've been doing with polynomials, characteristics of graphs of polynomials, and behaviors, multiplicity, what that meant for a 0 of a polynomial, what was happening on the x-axis. We just looked at graphing the rational inequalities. So looking at, let's say, one of the following. let's say you had x cubed plus 2x squared minus 3x is greater than 0. So solving nonlinear inequalities are different. And so when we were solving quadratic equations or quadratic inequalities, it was different than the linear ones. This is not linear. And so the first thing you want to do is get everything to one side. And that's what we were doing when we were graphing it. It's already to one side. And then we want to factor this. So once you get everything to one side of the inequality, what you're going to do is you're going to find the values which make that one side equal to 0. So I'm looking at x cubed plus 2x squared minus 3x and trying to figure out when is this equal to 0. So let's try to factor it. There, x is in common for all three terms, so we can pull out an x. We have x times x squared plus 2x minus 3. That is all equal to 0. And then I noticed that the trinomial inside that parentheses can also be factored further. So the number that multiplies to give us -3 and adds to give us 2, that's a +3 and a -1. So we can factor that as x plus 3, x minus 1 equals 0. So x is equal to 0, x is equal to -3, and x is equal to 1. So the values would set your inequality equal to 0 once you've gotten everything to one side. These are called your critical numbers or critical values. It depends on your book. And I kind of use that interchangeably, that terminology. So these are your critical numbers. So technically, we just found the values where it's going to be crossing the x-axis, right? And so if we looked at this, these are the values we want to see. Are our graph going to be below or above the x-axis on each side? And so what you want to do is you want to plot those numbers. I tend to plot them different. People do a little differently. So I plot it on the number line. So we have -3 is smaller. Let's do 0. -3 and 1. I know that these values, because my inequality is strictly greater than 0, I'm not going to include it in part of my solution. I'm not sure, though, what's going on the left or the right, so I don't know which way to mark my parentheses. Are they going to be opening up towards my negative infinity or positive infinity? So it might be helpful if we put an open circle there. Because it's not going to be included in part of our solution. Okay, so we want to, once you plot your critical numbers on your number line, which we can think of as our x-axis, we were going to graph this, you want to test on each side. So you want to plug in a value on the left of -1, and you can, I'm sorry, -3. So choose any number to the left of -3. It doesn't matter. Anything that you choose to the left of the -3, you're either always going to be positive or always going to be negative. And so if we chose -4, I think smaller numbers are easier. And so if we choose x equals -4. So if we go back in and we plug in -4 into this equation, we want to see what value we get back. technically we really only want to see if it's positive or negative. So we can kind of think of and use the factored form if you want. So if we plug in -4 in for x, we get negative, a negative number. -4 plus 3, that's a negative number. -4 minus 1, that's also negative. So if we multiply 3 negatives together, that's a number that's smaller than 0. So that tells me my graph on the left of x equals -3 falls below the x-axis. So we can think of our graph as coming up like this, if I was going to graph it. Well, we can use some of the reasoning that we learned earlier in this chapter by thinking about the graph. So all these multiplicities that made this 0 were values of multiplicity 1. They didn't occur, those factors didn't occur more than once. If our multiplicity was odd, it crossed the x-axis there. And so instead of coming back down and dipping, this is going to go above the x-axis. I can do that same sort of reasoning. I usually have my students without doing that reasoning, but we can, because we have already learned that. We can, I would tell them, choose a number in between that critical number and the next critical number. And so you would have to choose some number between -3 and 0. Well, if I chose x equals -1, and I plugged it back into the factored form's a little faster. So -1, negative number. -1 plus 3 is positive. -1 minus 1 is negative. So notice this does give us something that's above the x-axis. But again, let's do that reasoning that at x equals 0, that's only a factor that only occurs once. And so again, this is going to have to go below the x-axis, turn around, hit our number. And so if you chose any number between 0 and 1, you'll notice that you're going to get a negative number. So if I chose -1/2, well, -1/2, well, that's negative. -1/2 plus 3 is positive. -1/2 minus 1 is negative. Multiply that all together, it's, ooh, did I do something wrong? Yeah, no.
Why is it -1/2? Shouldn't it be just 1/2?
Yeah, it's negative, so maybe my reasoning is wrong there. Negative, hold on, just bear with me 1 second. Okay, so this is actually positive, right? So this falls above the x-axis. Okay, so that's, I don't like that, because it's telling me I can't use the same reasoning that I was doing before. Something to me seems off.
But you said it's between 0 and 1, so wouldn't it not be be positive 1/2?
Thank you, that's where I'm off.
All right.
So plug in positive 1/2. Is that what you were trying to say before? Someone else, it was a little bit muffled that you were trying to say. So if you plugged in positive 1/2, that's positive. 1/2 plus 3, that's positive. And 1/2 minus 1, that's negative. There we go. And so this was less than 0, which I was saying that it should be. And thank you, it is. And now choose anything greater than 1. Anything greater than 1, we can reason again about the multiplicity that it should be above. Before, you would have to test a value to the right of that critical number. So let's say x equals 2. So 2 that's positive. 2 plus 3, that's positive. And 2 minus 1, that's positive. This is greater than 0, and so this falls above the x-axis. Okay, so we were looking at when is f of x, or this function, greater than 0. So if we're looking at when is this greater than 0, we can see where the graph is going to fall above the x-axis, and we can see where the graph is going to fall. That's where we want. Pieces where it's going to be above the x-axis. And so we can see that that's every value in between -3 till we hit, was that the 0? Yeah. Yeah, 0. That was 0. So -3 to 0 is all above the x-axis. And then also when we're greater than 1. So 1 to infinity. So any number that you chose here would give us a true statement for this inequality. And if we graph the function x cubed plus 2x squared minus 3x, and we looked at that graph and where it was falling above the x-axis, it would be for these x values. So let's look at one more. And now let's, knowing about the multiplicity, let's use that to help us. Let me just do this one because it might throw people off. Let's look at x minus 3 as a factor. That factor times the factor x plus 2. This is, let's say, greater than or equal to x squared plus 3x plus 5. Okay, so just like if we were going to solve this as there was an equal sign, we would unfortunately have to distribute everything out and then get everything to one side and combine the terms. This says, well, this one isn't going to be bad at all. Okay, and I'll explain why in a second. So if we distribute this all out, x minus 3 times x plus 2, well, this would give us x squared. So our middle term is going to be a -3x plus a 2x, which is minus x. -3 times 2, our constant is -6. This is greater than or equal to x squared plus 3x plus 5. So first thing I see is that this is quadratic, nonlinear, and I would have to get everything to one side of the equation. But once I start moving things over, I notice that my quadratic equation quickly cancels out, or inequality, and now it becomes a linear inequality because when I subtract x squared on both sides, that goes, my x squares cancel. So we actually approach linear inequalities different than nonlinear inequalities. So this is where we got all the terms with the variables on one side, all the constants on the other side. So if we subtract 3x on both sides, add 6 to both sides, well, this would give me -x minus 3x is -4x. This is greater than or equal to 5 plus 6, which is 11. Divide both sides by -4. This is where you have to be careful. We're dividing by a negative, so our inequality is flipping. It's less than or equal to. 11 divided by -4. Okay, so we actually can see that our solution is x, we don't even have to test anything, is less than or equal to -2 3/4. They put this in interval notation, and so we're looking at everything from -infinity to -2 3/4. And we're putting a bracket because we're including, because it's equal to the value which sets it equal to 0. Okay, so rational inequalities. So when we were graphing rational functions, things could happen on each side of our vertical asymptotes. So knowing where your vertical asymptotes are going to occur are helpful for figuring out what are the solutions for our inequalities. And so if you have the following, I'm going to start with a harder one. Let's say you had 5 is all over x minus 3, and this is greater than 3 over x plus 1. I'm shocked at what time it is right now. I'm surprised it's already this late. I guess time flies when you're having lots of fun. So for rational inequalities, we want to get everything to one side of the inequality. So same sort of idea when we were doing the non-linear polynomials, we were getting everything to one side of our inequality. So first step, and this should hopefully is review, you're going to get everything to one side and rewrite it as a single fraction. Okay, so I noticed by doing that I'm going to need a common denominator. So when I bring over and I'm going to subtract 3 over x plus 1 on both sides. But while I'm doing that, I'm going to rewrite this with common denominators. And I notice my common denominator is just x minus 3, x plus 1. So I'm going to have to get a common denominator for the piece on the left of my inequality, I'm going to have to multiply this by a fancy 1, x plus 1 all over x plus 1. So minus, so moving over the 3 over x plus 1. But again, I want a common denominator so I can combine this as a single fraction. And so what's missing in my denominator is my x minus 3. So I need to multiply by a fancy 1, x minus 3 over x minus 3. It would be silly of me if I canceled here, because that would just undo what I was just doing. And a lot of times students want to do that. And this is all greater than 0. So we're going to have to combine like terms in our numerator. So first thing we want to do is distribute. So distributing my 5, I have 5 times x is 5x, and 5 times that plus 1, so that's plus 5. I have a common denominator, so I can rewrite this as just a single fraction. And then be careful, because of that minus sign outside of this, between our fractions, when you're distributing that 3, you're actually carrying the negative with a 3. And so you're actually distributing -3. So -3 times x is -3x. And -3 times this -3 is a +9. And we're still looking at when is this greater than 0. So let's combine like terms. 5x minus 3x is 2x. 5 plus 9 is plus 14. This is all over x minus 3, x plus 1, which is greater than 0. Okay, so when we're graphing these, we talked about seeing if a point fell above or below the x-axis, looking at either side of the vertical asymptotes. I can tell that I have vertical asymptotes at x equals 3 and x equals -1. And so these are actually critical numbers for testing for rational inequalities. So the values, even though they're not defined there, are critical numbers. So x equals 3, x equals -1. Also, where our x-intercept was. That's a place where our graph could be crossing the x-axis. And so it could be jumping signs. And so 2x plus 7, looking at when our numerator is equal to 0, that's equal to when x is equal to -7. So these are critical numbers. And again, that's when your denominator is equal to 0 and when your numerator is equal to 0. So technically, we can't ever include the values what set our denominator equal to 0 because that's not part of our solution. So if I had had an inequality in here with an equal sign, I would not include those. I would only include the part that let my numerator equal 0. We can only do this when it's a single fraction. One error is students like to cancel fractions with inequalities. And if you did that, if you multiply both sides by your LCD there, then you don't see those critical numbers that set the denominator equal to 0 and where our vertical asymptotes would be if we graph that function. Okay, so same idea. You're going to plot those on a number line. We can use what we just learned to help us instead of really having to go through and plot points or plug in values to see if it was true or false. And so let me plot my critical numbers. So smallest is -7, then comes -1 and 3. We knew that these were asymptotes. Maybe if we put that there, that might just help us. And so if we look at x equals -7, we want to see if something to the left of that falls above or below the x-axis. And so doing that, choose any number to the left of -7. So let's say x equals -8. So again, we're not really worried what number we get back. We're just worried, is that going to be a positive or negative number when we plug it back in? And we're looking at the one where we had everything greater than 0. So if I plug in -8 into my numerator, I get -16 plus 14. So that's a negative in my numerator, all over -8 minus 3, that's -11. So negative times -8 plus 1, that's negative. So I notice that a negative over a positive, this is going to be less than 0. So technically our graph is going to be below the x-axis here. So I guess we could, if we were graphing it, we knew what's coming up. So same sort of reasoning as a below, or before with our intercepts, and is it crossing or touching? If you look at it, x equals -7 is a odd multiplicity. It only has one factor, and so it's going to go above the x-axis here. So between -1 and +3, I don't have any x-intercepts. We already found all the values which set this whole thing equal to 0. I need to test a number in between -1 and 3 to see if my graph is going to fall above or below the x-axis. So let's choose x equals 0. That's the nicest one. And so if we plug it in, the piece before okay. If I plug in 0, I get 14 in my numerator, which is positive, all over -3 times +1. So a negative times a positive is negative. So this is less than 0. So I know my graph is in here somewhere, kind of like a parabola shape. And then I'm going to choose something that is bigger than 3, which is 4. So I know that on this other side of 3, because of no other critical values or x-intercepts, that it's either going to be strictly above or below after 3. X equals 4. If I plug it in, I get a positive number in my numerator, and I'm going to get a positive number in my denominator. Positive times positive in the denominator is greater than 0. And so it's going to be above the x-axis. So I actually kind of graphed it while we were doing this. Our question was asking, when is this piece above the x-axis? I want to change this to be with the equal sign so I can stress again what we kind of talked about. If it doesn't have the equal sign, it's easy because you don't have to include any of your your critical numbers when you're doing this. But if you have an equal sign in there with a rational function, we can't have the value set the denominator equal to 0. And so we're looking at, when is our graph going to always be above the x-axis, or when are the values of x going to make this positive? And so this would be at -7, but -7 sets the whole thing equal to 0, and so 0 can equal 0. And then we're going to go all the way up to -1, but we're not going to include it because that was an asymptote. And then union, any number that's bigger than 3 would work. And so, but we can't include 3, again, because it's an asymptote or a value where it's undefined. And we're going to infinity. So we got our solution to our original rational inequality. So any number you plugged in there that falls in that set or that interval of x values should give you a true statement back. Anything that falls outside of those numbers should give you a false statement. Okay, so we just finished 5.5 and we got to where I needed to get to. Next week, so we're not meeting tomorrow. It's a holiday. We're observing for 4th of July. And I'm just gonna, let me turn this off. So I hope you guys have a good weekend, but I'm not gonna let you go yet.